Hello again, Chem students. Today we're going to talk a little bit about molecular models and prepare for ChemActivity 6. Now there are a couple of different kinds of models you might have purchased. One would be the stick model shown here. Its individual pieces look like this, and you would want to snap two of the sp3s together and snap them together firmly, and that makes a tetrahedral center. Right now I've built the butane, the 4-carbon molecule. And just to show you what this represents, here's a carbon with its attached hydrogens in a tetrahedral shape, a second carbon, a third carbon, and a fourth carbon. Alternatively, you might have a set of balls and sticks that look something like this. Generally, those are put together by snapping, taking the tetrahedral pieces for tetrahedral carbons, snapping the hydrogens and the bonds together. And you want to use the rigid bonds, the shorter rigid bonds for making these bonds. If by chance you were to pick a bendy bond, one of these more flexible bonds, you would find that it's very difficult to get a rigid conformation. You get a lot of wiggling going on. The bendy bonds actually have a purpose. They're for making pi bonds, or the second bonds between two atoms, double bonds. And we will, of course, be using that later in the course. But for today, we are going to use only the rigid bonds. Okay, regardless of the kinds of models you have, what we're going to be doing today is looking at rotation around the sigma bonds. For example, on a butane, you can rotate between the first and second carbon atom, the second and third carbon atom, or the third and fourth carbon atom. You can also see that rotational thing taking place with the stick models. In fact, this is one of the areas where stick models work very, very well. Normally, when we talk about this rotation, we can represent the molecule several ways, but we often choose to look right down the bond we're looking around. In this case, 1, 2, 3, 4, we're going to look down the 2,3 bond, the central bond. And as we rotate, say the front group relative to the back group, you can actually very clearly see what's going on around that bond by looking down the bond. Okay, for example, in this conformation, we have a large group right here on top, the large group right here on the bottom, and these hydrogen atoms sticking out at an angle. And if you measure that carefully, you'll find that if we projected this flat, the so-called Newman projection, each of those angles between one and the next hydrogen is 60 degrees. We can do the same kinds of things with the ball and stick models, in which we rotate around. Again, I'm looking down the central bond. In this particular orientation, I've lined up all of the bonds. This is called an eclipsed conformation, just like an eclipse of the sun or moon involves things lining up. I can rotate a little bit to a so-called staggered conformation. In this particular staggered conformation, the two methyl groups, the two large groups that aren't attached to the bond being rotated, are 60 degrees apart from each other and might start to feel a little bit of steric repulsion. Okay, steric means that things are trying to take place in space. Torsion means that bonds are lined up. So this particular conformation has a lot of torsional strain between the front and the back bonds. A bond with its electrons is repelling another bond with its electrons. Although there are the plastic models are the first choice for manipulation, and I will have a few sets available for checkout if no one in your group has one. There is an alternative as well for at least some of the functionality. Here is the URL chemmagic.com web molecules here, but you can start out with ethane, and you can rotate it so you can look down the bond just like you can a plastic bond. You can build from it, add carbons to it. If I wanted to build a carbon here, I could make carbon propane and then rotate it and look down each of its bonds. I could butane, for example, I can put a carbon substituting for that hydrogen right there, and this will allow me to make what we call gauche butane, one in which the two methyl groups are starting to occupy the same space. This one also has the ability to put an electron cloud on it, so you can actually see when electron cloud areas are getting very close and repelling.
So it has some strengths to it. It does not allow you to rotate around sigma bonds and end up with eclipse conformations like you can with a plastic model. There is one other site that I want to point out for conformational analysis, and again, if you bring a laptop or tablet, web-enabled tablet to class, one that can run JMOL, you can also see this. This is one's from University of Calgary, and I will put this link as well as the other link on our Blackboard site. This particular page has a series of models that you can rotate and move around. For example, here's ethane in a staggered form. If you look down the 2,3 bond, the hydrogens are staggered relative to each other. It also has eclipsed ones that you can rotate around, so all the extremes are here. And it has an animation of this process. So for example, you can imagine rotating around a CC bond. We're looking down one of the carbons, and as I rotate, you can see anytime the bonds are all lined up, so-called eclipsed, you have a high energy conformation. As you start the animation and it moves away from eclipsed, you go down in energy, but then as you move back towards eclipsed again, as you rotate another 60 degrees, you go back up in energy. And for every 60-degree transformation, you go from a high to a low energy point. To the next page of this sequence, you'll also see the same thing for butane. Here's a butane molecule, and again you can rotate it so you're looking right down any one of the bonds. In this case we have, if you look down the 2,3 or central bond, you're going to see an anti-eclipsed conformation, and you can move it around. It's got some still conformations here. You can see the gauche conformation by rotating it. You can see the syn all eclipsed conformation, and once again there is a moving animation where you can see energy versus rotation. Now with butane, looking down the central 2,3 bond, you can see there's a variety of different forms. There's not just eclipsed and staggered. There's two kinds of eclipsed and two kinds of staggered. For example, if you stop at when everything's lined up, including the two methyl groups, you'll see that's the highest possible energy conformation. If you move to the gauche conformation, which is rotating by 60 degrees, we now have staggered bonds, but two methyls that interact with each other through space, sterics. If you move another 60 degrees, you're back to eclipsed, and you're at the top of the energy graph of some sort. It's a local maxima. It's not as high as the syn fully eclipsed. And if you continue all the way to 180, from the original, you end up with the two methyl groups very far from each other in space and all of the bonds with a 60-degree dihedral angles. This one's called anti and is the lowest possible energy.